to now look at the idea of statistical independence, distinct from political independence. Statistical independence refers to the connection between two variables. And I'm going to use the example from cards, playing cards, 52 cards in a deck. And we've got spades, diamonds, clubs, and hearts. And imagine that I'm looking at, say, a queen. I tell somebody to take a card from the deck, and whether it's a king, a queen, a jack, something like that, and a specific suit. Now, if I tell you that it's a queen, that doesn't help you to know whether or not it's a club or a diamond, because knowing that it's a specific card doesn't tell you which specific suit it might be. In this case, we say the connection between the two variables is independent. In this case, the two variables are what the specific card is and what the suit is. If, on the other hand, I tell you that the card is, say, it's a red card as opposed to a black card, well, then that's going to adjust whether you think it's a specific suit. Because no, it's a red card, it has to be either a diamond or a heart, and if it's a black card, then it has to be a spade or a club. In this case, we say that the variables are not independent. So the notion here is that, does it provide useful information? Are you going to adjust your prediction of what the other one is? So as I say, independent means knowing the value of one variable, whether it's a king, queen, or something like that. Doesn't help you to predict whether it's a specific suit, but knowing the color means that you can maybe predict or alter your prediction of what the suit happens to be. If two variables are independent, then we say that they have no connection. Knowing one doesn't help you to talk about the other. That means also there's no correlation and there is no causality between them. I want to look at this concept of correlation and causality in a moment. So if we talk about two quantitative variables, let's call them variable A and variable B, then it is possible, if they're quantitative variables, to calculate a correlation. If the two variables are independent, meaning you say knowing one doesn't help you to predict the other, then let's consider, for example, variable A and variable B. Let's say the grade on a test and the height of a student. Normally you'd expect that knowing one doesn't help you to predict the other. We say then, note that both of these variables are quantitative, we'd say that we'd expect the correlation to be 0. If the two variables are not independent, then and they're both quantitative variables rather, then they could have a positive correlation, which means sometimes referred to as a direct relation. If one variable is greater, then the other one should also be greater. For example, the height of a father or a parent and the height of a child. Not always, but generally you speak that if the parents are tall, then the child might also be tall. It can also have the situation where there's a negative correlation, sometimes also referred to as an indirect relation. For example, say the variable A is the outside temperature in winter, and the variable B is the consumption of electricity. So in this case, if it gets colder outside, then people generally use more electricity to heat their homes. So it's a negative correlation. Make a little point here that I'm discussing here something called a linear correlation. That means to say that as one gets bigger, the other gets smaller, or they go both in the same direction. There's something called a nonlinear correlation, which means that the connection between the two variables is rather complex. And temperature provides a good example. So that in the case of the winter, it's true, if it gets colder outside, then people consume more electricity. But of course, in the summer, it's a direct relation. Meaning you say that as the outside temperature rises, people use more electricity because they may run their air conditioning longer. And so the connection between the temperature, outside temperature, and the use of electricity is a rather complex relationship, and we've referred to this as nonlinear. In this course, I'm going to be looking at primarily a linear correlation because it's easier to understand. But of course, the correlation between two quantitative variables can be a little bit more complex than linear. I want to briefly talk about this notion of causality, which is much more complex. In the sense of causality, we're saying that, well, one variable causes, we often refer to this as the independent or explanatory variable, causes or controls for the dependent variable. Now, in order to establish causality, we'd have to have some kind of model or theory that explains why, and notice the word explain, to explain why one variable alters the other one. Meaning to say, too, that if we're capable of controlling this cause, then it means that we can alter the effect or the dependent variable. Again, we'll look a little bit at this question a little bit later in the course, but this goes beyond, really it involves, in a sense, some kind of a model or theory about the behavior, the social behavior we happen to be looking at. Lastly, obviously, most things that happen in the real world have more than just simply two variables. They have a third, fourth, fifth, sixth variables. And sometimes we invoke the notion of something called ceteris paribus, which means to say we're going to keep everything else constant. We're only looking at two variables, the relationship between the two. This is a theoretical concept. Control variables refer to these, sometimes also called instrumental variables. These refer to these other variables that could be somehow excluded. So just some quick examples here of how we might be looking at the relationship between two variables. Take, for example, mother tongue, the person's first language spoken, and the province of birth in Canada, or person's citizenship and their religion. Around the world, it's often the case that people in certain countries have certain religion, not always, or something like, say, eye color and income, or the diploma achieved in income, how much education a person has. Think of height of person, how tall a person is, and their income. In this first example I've given at the top here, these are both qualitative variables, and that's what we're going to be looking at in this example today with statistical independence and the notion of something called a chi-square test. But then you can also have cases where the examples down below are both quantitative variables, in which case we'd be looking at something like correlation. But you can combine both of these together. For example, eye color is a qualitative variable. It could be related to income. And then there are methods in which to test for independence with these two, a variety of methods that are kind of like a combination of correlation or just simply statistical independence. And then, of course, you can have many cases like famous one, political party affiliation and things like income, age, language. There's a whole variety of ways to relate two variables. And then you have vague things like health and pollution. How do you define the health of an individual? How do we define air pollution or water pollution and so on? One of the first ways we'll be looking at this concept of a test of independence, and the idea of independence, we'll be using something called the chi-squared test of independence. Notice how it's spelt. It's E-C-H-I. It uses the Greek letter chi, and it's pronounced chi-squared. This is typically a test of the independence of two qualitative variables. And the way we're going to do this is we'll have, let's call it variable A, the eye color of a person, and let's call variable B, the continent of birth of the person. So we have two qualitative variables. We'll collect data, put it into some kind of a table like we've got here. I don't have the data. I'll just write in here because we'll be collecting data. Data will be added in this table. And then from this table of data, we'll determine something called the degrees of freedom. And then we'll also calculate what is called a chi-squared statistic. I want to just pursue this a little bit more to take a look at what this might look like. Here we've got the chi-squared distribution, and you'll notice that it has a positive skew. And it also starts at 0. So the chi-squared distribution is never negative. We've got the chance proper density on the vertical axis, and then we've got this chi-squared statistic on the horizontal axis. The area, believe it, is 100%. Now, the degrees of freedom, let's say for the sake of argument, are equal to 4. We'll look at later how these are determined. Once we've determined this chi-squared statistic, let's call it 11.4, you'll notice that will divide the entire distribution into two parts. So I've just done this arbitrarily. Let's say the partial on the right is equal to 17.8%. That's the area underneath the curve. The area underneath of the curve on the left is 82. Just make up these numbers. This area on the right, this white area, can be sometimes referred to as the significance level, or sometimes referred to as the p-value or PROB value. Now, this chi-square distribution can lead to two methods of testing. This is a test of independence of two qualitative variables. One is what's referred to as a classical test. Watch the order in which we conduct this test. First, of course, is to determine the degrees of freedom, which we'll look at in a moment later from the table of data. Then we decide in advance, this is a classical test, we decide in advance what's called the significance level. For example, we arbitrarily pick a number like 15%. That means to say we determine the area on the right will be 15%, and the area on the left is necessarily 85%. How is this determined? This is done by the person conducting the experiment. In advance, they decide that the significance level of the test is going to be a set percentage, anywhere between 0 and 100%, often a relatively small number. Then, from the table, That means to say, using the chi-squared distribution, we find a critical number. Call it a critical chi-squared statistic. This will be determined from the table. We'll be doing this later. And then we use the table, or rather the data, we use the data to calculate a test statistic, and we decide whether it is greater or less than this critical number. If it's to the left of this critical chi-squared value, we say we accept the null hypothesis, or more correctly, fail to reject the null hypothesis. And if the number we've calculated from the data is to the right, we say we reject the null hypothesis. This is a classical test. There's another way of doing this test, which is referred to as the PROB value, in which case, once again, we determine the degrees of freedom from the data. In this case, though, we don't predetermine a significance value. We simply use the data to calculate a test statistic. Let's say, for example, we get the number 8.7, in which case now we look up from the table, we determine what the white area is on the right, and we refer to this as the PROB value or a p-value. So it's not like a classical test where you accept or reject the null hypothesis. You simply calculate from the data test statistic and then report the p-value or the PROB value. We're going to be doing both of these types of tests.
Der hat Zähne und die trägt im Gesicht. Und McKeith,